In this video, I'm going to talk about how to find test statistics and p-values. So first of all, a test statistic is a random variable that is calculated from sample information given in a problem. So we're going to compare this sample information to our null hypothesis and alternative hypothesis to see what we can conclude about the parameter that we're testing. So let's suppose I want to test the claim that the average distance a statistics teacher can jump is 1.4 meters at the alpha equals 0.05 significance level. And suppose that we've actually calculated already that the test statistic is z equals 2.33. So what does that mean in our problem? Right now I'm not going to talk about how I calculate the test statistic. I'm going to assume that it's already calculated and we're going to see what it means in terms of the problem. Then we'll talk about how to calculate it. So I start by writing down my null and alternative hypotheses. So my null hypothesis says that mu is equal to 1.4. The alternative says that mu is not equal to 1.4. I draw my normal distribution, and I have a significance level of alpha equals 0.05, and because this is a two-tailed test, we're going to cut alpha in half and we get 0.025. So our critical values are z sub 0.025 and negative z sub 0.025. And we calculate those using inverse norm, and I get plus and minus 1.64 for the critical values. So now this is where we want to use our test statistic. We're going to compare our test statistic to the critical value. Either the test statistic can fall in the center, which is not the rejection region. So here would be the center of the distribution. If it falls anywhere within this area, then that means that the sample information is not falling significantly far away from the value in the null hypothesis. So we're not going to say that we proved the null hypothesis, but we did not disprove the null hypothesis. If instead, let's change the color here. Okay, let's say that the test statistic falls into one of the tails. That's our rejection region, so that's where we would conclude that we should reject the null hypothesis. So let's see, what do we have in this particular problem? Make some space, shade in our critical regions, and we can see that our test statistic is falling at 2.33. We were given that in the problem, and that is falling into the right-hand tail because 2.33 is greater than the 1.64 for the critical value. So this means that we should reject the null hypothesis in this particular problem. So that test statistic is falling significantly far out into the tail. And so we reject the null hypothesis. Let's take a look at another problem. Here I want to test the claim that the average distance a statistics teacher can jump is 1.4 meters, again, at the alpha equals 0.05 significance level. And in this case, your test statistic is t equals negative 1.44. That means we were using the t distribution in this particular case, and that's why I need to know the sample size, which is 20. So again, I have my null and alternative hypotheses, and now I draw my t distribution. Looks pretty much just like the normal distribution. And, man, it's going a little too fast. Okay, let's see. So this is the t distribution. Alpha is 0.025 or 0.05. it's a two-tailed test, so we cut alpha in half, and we're calculating t sub 0.025 and negative t sub 0.025. So we can find negative t sub 0.025 by using the inverse t function in the calculator. We put in the area in the tail, which is 0.025, and then the degrees of freedom, which is 19. Since the sample size was 20, we just subtract 1 from that, and we put in 19 for the degrees of freedom. And that gives me negative 2.09. So negative 2.09 is going to be my lower critical value. 2.09 is the upper critical value. And now we see that our test statistic is falling in the center. It is not in the rejection region because our test statistic is negative 1.44. So since it's not in the rejection region, we do not reject the null hypothesis. So how do we calculate our test statistic? We're going to use the graphing calculator to do this, and depending on the problem, you may be working with a proportion and you're going to use one prop z-test. It may be a mean with sigma known, and then we use the z-test. And if we are testing about a mean and sigma is unknown, then we use the t-test. So I'm going to use one of those, and whichever is appropriate for that particular problem. So you're looking for clues in terms of the problem will say, test the claim that the mean value is greater than this or something like that, and then you know it's about a mean. Or if they say average, again, it's about a mean. If they say test the claim that the proportion is such and such, then we know that we're doing a one prop z-test. Okay, so now let's take a look at this problem. Keep going. Test the claim that the proportion of people who are currently binge watching Game of Thrones is greater than 20%. And we know that in a sample of 2,500 people, 524 said that they are currently binge watching Game of Thrones. Use alpha equals 0.05. So this is asking me to test a claim about a proportion. So I'm going to set up my null and alternative hypotheses as we did before. The null hypothesis is that p is equal to 0.20. The alternative is that p is greater than 0.20. And so that tells me that this is a right tail test. And since it's about a proportion, we're going to use one prop z-test. So for the one prop z-test, I'm going to put for p sub 0, that's 0.02, 0.20, sorry about that, 0.20, because that's the value from the null hypothesis. So whatever the value is in the null hypothesis, that's what goes in there for p0. X is the number of successes, and that's 524. N is the number of trials, and that's 2,500. And then we put our alternative hypothesis, and since our alternative hypothesis said greater than 0.20, I'm going to choose greater than, well, actually in the calculator, let's fix this. It's greater than 0.20, but in the calculator, it's going to say greater than p0, okay? And that p0 value is, of course, that. So the direction of the inequality is not going to change. Whatever you put in your alternative hypothesis here, that's going to be the same here in the calculator. All right, so what are the results? I get a test statistic, z equals 1.2. It also gives me a p-value. We haven't talked about p-values yet, so I'm leaving that out. So my test statistic is 1.2, and that's how I find the test statistic. And now I can compare that to my critical value of 1.64, and since 1.2 is not falling in the rejection region. Here's my 1.2. So we do not reject the null hypothesis. All right, now let's look at this problem where we're testing the claim at the alpha equals 0.01 significance level that the average distance a statistics teacher can jump is 1.4 meters. Assume that sigma is equal to 0.2 meters and we have sample data that's being given. So the first thing I'm going to do is I'm going to take this data and I'm going to put it into L1 in the calculator. Okay, so make sure your sample data goes into list 1. You can use other lists, but then you're just going to have to adjust along the way. So I kind of assume in all of these videos that we're just going to go ahead and use L1 for these. All right, so I write down my null and alternative hypotheses. I put my data into list 1, and then I'm going to run a z-test because we knew sigma. Wow, that's going really fast. Let's pause that for a moment. So we're running a z-test because sigma is known. The input is data because we entered our data into list 1. Mu0 is the value from the null hypothesis, so that's 1.4. Sigma, we were told, is 0.2. The list we should use is L2. The frequency is 1. I just skip over this. You don't have to type 1 in there. You just want to skip right over that. And then your alternative hypothesis is that mu is not equal to mu0 because that's our alternative hypothesis was a two-tailed test. So when I choose calculate or draw, my result is that the test statistic is z equals 2.14. Since it's a z-test, our test statistic is going to be z equals whatever. In this case, it turns out to be 1.24. And now I can compare that test statistic to the critical values we get. And we have critical values of plus and minus 2.58. So that tells me again, my test statistic is falling in the do not reject area. So we are going to not reject the null hypothesis. And that's my conclusion. All right, here's another example. Again, about the average distance a statistics teacher can jump. And in a sample of 28 statistics teachers, the average distance jumped was 1.9 meters with standard deviation 0.3 meters. And we're using a significance level of 0.02. Okay, so again, I'm going to write the null and alternative hypotheses. And then I'll need to decide what type of test that I'm doing. It's about a mean, because we're talking about average. So the question is here, do I know sigma? And a lot of times people think that, oh yes, I know sigma because I see standard deviation, and sigma is the standard deviation. Sigma is the population standard deviation. But in this sentence, it started out by saying, where did that standard deviation come from? It came from a sample. It came from a sample. So this is x bar is equal to 1.9, that's the sample mean, and S is equal to 0.3. So this is the sample standard deviation. It is not sigma. We have to do a t-test. So watch out for this. This is the trickiest thing that you'll see with a t-test, is that you'll think that you know sigma, but you do not know sigma. All right, so here's my null and alternative hypothesis. And we're doing a t-test because sigma is unknown. My input is stats. Mu0 is again 1.4. And now we have the values for x bar and S. And in the calculator, it always says SX, but that's all right. And we put in 0.3 for that. And our sample size is 28. Remember, n is the sample size, so we're not going to use degrees of freedom here. I know that's a little confusing. And mu is not equal to mu 0. So we'll choose calculator draw on that. And when we do, our results are that the test statistic is 8.82, and that is falling way far into the right-hand tail, so we are going to reject the null hypothesis in this particular case. That makes a lot of sense, because if the average person is jumping 1.9 meters when we were saying 1.4, that seems like a really significant difference. So that does make sense. Okay, now let's talk about p-values. So a p-value is the probability that a value would fall at least as far out as the test statistic, assuming that the null hypothesis is true. That is not a very helpful definition for p-value. So the p-value is really just the probability of falling at least as far as your test statistic. If we are talking about a z-test or a one-prop z-test, then we are going to calculate this p-value, or we could calculate the p-value by using the normal CDF function, because it's a probability and it's really just how far are you going out into the tail past that test statistic. So the idea behind using the p-value is that we want to compare that to our significance level, and it winds up being a lot easier to compare the p-value to the significance level rather than having to draw the distribution every time. So while I can use the normal CDF function here, and I would use the t distribution, I would use tCDF in the calculator. I don't really need to do that because the calculator is going to find the p-value for you. So when we do our z-test or one-prop z-test, in theory, we could use normal CDF in those cases, but we're not going to do that. We're just going to have the calculator find the p-value for us. So how do I use the p-value to form the conclusion? So what I'm going to do is I'm going to compare that p-value to the significance level alpha. If p is less than or equal to alpha, that tells me to reject the null hypothesis. And if p is greater than alpha, I fail to reject the null hypothesis, or I do not reject the null hypothesis. So let's see this in action. We're going to test the claim that the average distance a statistics teacher can jump is 1.4 meters using alpha equals 0.05, and the p-value is 0.0316. So what does this mean? We have p is 0.0316 and alpha is 0.05. Since p is less than alpha, we're going to reject the null hypothesis. Now, while I don't have to draw my distribution, let's take a look at what this means. We've been doing a two-tail test here, and so I have my normal distribution, or t distribution. It doesn't really specify in this particular scenario, and it doesn't really matter terribly. So my critical value, I don't know, because I don't know which distribution we're using, but I do know that the area in each tail is 0.025. So in this case, I don't really need to know which distribution it is that I'm using. So I'm just going to consider this 0.025. And my p-value is 0.0316. So what I can do is take that and divide it by 2, and I get 0.0 158. Sounds right. And so what does this mean? It means that the p-value is going to take up less space than our significance level. So the p-value is smaller than alpha. And if we had calculated our test statistic, this would be the negative of the test statistic. This would be the positive version of the test statistic. And so you can see that drawing the diagram is less helpful in this particular case. It's a lot easier to literally just look at, is p less than alpha? Yes, then we reject the null hypothesis. If p had been greater than alpha, then we would not reject the null hypothesis. And so I don't have to go through all of that drawing of a diagram there. Now let's try another scenario. Again, testing a claim about the average distance a statistics teacher can jump. And here we have the p-value is 0.0724, and we're using alpha equals 0.05. So since in this case the p-value is greater than alpha, I will fail to reject the null hypothesis. So that's how test statistics and p-values work. And you can see the little tutorials on Canvas for how to use the particular different types of tests that are in the calculator.